Capacitors. Today we will be studying about capacitors. So what is a capacitor? A capacitor is a device which is used in electric circuits. Let us look at a couple of uses in everyday life. One of the most common uses is tuning a particular frequency in our radio receivers or television sets. It is also used in automobile ignition systems to remove sparking. When an electric current is switched on or off, there is an induced current which can cause sparking in the gap. But if you put a capacitor over there, that current is used to charge a capacitor which can avoid the sparking in the gap. Supposing we have a conductor and we give it a certain amount of charge Q, then its potential rises. The greater the charge given, the greater is the potential. Or we can say that charge is directly proportional to its potential. Or rather, potential is directly proportional to the charge given to the conductor. We can also rewrite this mathematical relation as Q is equal to CV, where C is the capacitance of the conductor. What are the various factors on which the capacitance depends? It depends on the shape and size of the conductor, what is the surrounding medium around the conductor, and whether there are other conductors present around the given conductor which is in consideration. We can also rewrite the above equation as C is equal to Q upon V, or it is the same as the charge stored per unit potential rise in the conductor. The SI unit of the capacitance is farad, or 1 farad is equal to 1 coulomb per volt. However, farad is a very large unit, so we use smaller units like microfarad, which is 10 raised per minus 6 farad, picofarad, which is 10 raised per minus 12 farad, or nanofarad, which is 10 raised per minus 9 farad, and so on. Let us consider the capacitance of an isolated spherical conductor. Let us say we have a sphere of radius r, and let us say charge Q is given to the conductor. We can write that its potential is equal to Q divided by 4 pi epsilon naught r. We've already seen that C is equal to Q by V, or Q by V is equal to 4 pi epsilon naught r. Thus, the capacitance of a spherical conductor is C is equal to 4 pi epsilon naught r. Now, if we look at this expression, then we can see that capacitance is directly proportional to the radius of the spherical conductor. The larger the radius, the more is the capacitance of the spherical conductor. Let us look at the principle of a capacitor. Let us say that we have a very large plate which is a conductor, and we give a certain amount of charge to it. Okay, there is a limit to the amount of charge that can be given to the conductor, because as more charge is given, its potential rises, and beyond a certain limit the charge will start leaking. If we get another plate and we put it next to this given conductor, then on one side of the plate positive charge will be induced, whereas or rather the side which is closer, negative charge will be induced. This charge has to be opposite to the charge given to the plate, and the opposite side of the plate will acquire positive charge. Now this negative charge is going to reduce the potential of the plate 1, and the positive charge is going to increase the potential of the plate 1. But since negative charge is closer, so there is an overall decrease in the potential of plate 1, so more charge can be given to the plate 1. So if we, as the next step, if we earth the outer side of the second plate, if this is the side which is closer to it, if we earth the other side, then this positive charge will go to the earth. Now the capacity of the first plate to hold charge increases because there is a decrease in the potential due to the negative charge induced on the second plate. So capacitor is based on this principle. A typical capacitor, which is a parallel plate capacitor, is made up of two parallel plates which are separated by a distance d. So d is the distance between the plates, a is the area of cross section of each plate, and if plus q charge is given to one plate, there will be minus q charge on the other plate. How we charge this kind of a capacitor is, we can see an electrical circuit. This is how we indicate a capacitor in an electrical circuit. And let us say that this is a battery which is having a potential V, and this is a key. As we switch on the key, electrons from the first plate will start moving towards the positive end of the battery. That means the current will begin to flow from positive end of the battery and through the circuit it will flow to the negative end of the battery. Thus, the positive end of the battery will extract electrons from one plate and deposit them on the other plate. As a result, one plate will acquire positive charge and the other plate will acquire negative charge. This process is going to continue till the time the capacitor also acquires a potential V which is exactly equal to the potential of the battery. Then the current will stop. Now the capacitor has charge stored on it, and the potential difference across the plates is exactly equal to the potential difference of the battery, or charge stored can be written as Q is equal to, if C is the capacitance of the plate, V is the potential difference across it, then it is Q is equal to CV. So if a capacitor is charged, it stores charge. Also it stores energy as electrostatic potential energy. Thus, if charge Q is given to a capacitor of capacitance C, then the work done in doing so is stored as the electrical potential energy U in the capacitor.